In this module, we're going to talk about parametric curves, both in regular coordinates, in Cartesian coordinates, and in polar coordinates. So far, what we have looked at are graphs of functions for the most part. So things like that, curves that pass the vertical line test, in other words, each vertical line intersects a graph in at most one point. We've seen curves, studied curves that do not satisfy this condition, curves of the form f of xy equals 0, so for instance for the circle or ellipses or other kinds of curves that are defined by an implicit relation between x and y, in particular when we were looking at implicit differentiation in Calc 1, it was in part to find tangent lines to these kind of curves. However, we can think of curves as trajectories of something that moves. So for instance, this curve can be thought of as traced out by the motion of this blue point. Thinking of it that way, to trace out the curve, we're going to look at the coordinates of the blue point as functions of time. So the x-coordinate of the blue point is a function of time, let's call it f of t, and so is the y-coordinate. In that way, while we may restrict the time to a certain interval, in that way to a parameter t, which in this particular case, thinking of motion, we can think of t as time, but the parameter may be something else. We associate a pair of coordinates in the plane, x, y, which are two functions of time, so x and y both depend on time. And as the parameter goes through the interval of definition, to each t we associate the point of coordinates x of t, y of t, and going through all the possible values for t, we trace out a curve in the plane that we call in this case parametric curve, because it's given by parametric equations, namely x as a function of the parameter t, y as a function of the parameter t. However, if we think of the curve c traced out as t goes over the interval for the parameter, the parametrization f of t, g of t for t in I actually encodes more than the curves itself. It also encodes how we describe this curve, in what direction, at what speed, and so on. So a parametric curve has many sets of parametric equations or parametrizations. For instance, if we look at the unit circle and we're looking for a parametrization of this curve that has Cartesian equation x squared plus y squared equal 1, one way to parametrize it is to pick a point and rotate it along, and we want to just find a parametrization of this motion that describes the circle. So if we look at a particular position in this motion, here we have angle t measured in radian, and the corresponding point on the unit circle has coordinates cosine t, sine t. In other words, x equals cosine t and y equals sine t is a set of parametric equations for the circle, and if we restrict the parameter t, which in this case is the angle of rotation, to the interval 0 to pi, that corresponds to describing this curve once in the counterclockwise direction. Now, let me restart here to time t equals 0 or angle t equals 0. So when t is 0, x is 1 and y is 0, and as t increases, you see that x is going to decrease and y increase, and then y decreases, and so on. And so we describe the circle exactly once. Now, another set of parametric equations for the same circle would be to replace t by 2t in the equations, and then to describe the circle once we only need to have t between 0 and pi. So the effect of that is to describe the circle again once, rotating around the circle counterclockwise once, but this time we're going to go twice as fast. So this is what what is the effect of replacing t by 2t, we go along twice as fast. Of course, if we take the same parameterization with x is cosine 2t and y is sine 2t, but now we take t between 0 and 2 pi, we go still twice as fast as for the first parameterization that we have looked at, but this time we describe the circle twice. So overall, we go for the same time from 0 to 2 pi, but in that time we go around twice because, of course, we're moving twice as fast. Now let's look at another parameterization where, let's say, I switch the role of x and y. So x is sine t instead of cosine t, and y is cosine t instead of sine t. Well, then when t equals 0, x is sine 0, which is 0, y is cosine 0, which is 1, so we start at the point 0, 1 instead of 1, 0. And as t increases from 0 to, say, pi over 2, then the sign is going to increase from 0 to 1, that is x is going to increase from 0 to 1, while y is going to decrease from 1 to 0. And therefore, we're going to describe the circle clockwise by turning around the circle once clockwise. So you see that there are many ways to write parametric equations for the same curve. Now, how do we sketch a curve if you have a set of parametric equations? Let's look at an example where x is cosine t and y is sine 2t, and t is restricted to the interval from 0 to 2 pi. So what you should do if you want to sketch a curve, and we're going to say more in the next video, but to go for a rough sketch, you would draw the graph of the x as a function of t and the graph of y as a function of t. So this is x as a function of t, and this is y as a function of t. And then we're going to try to follow along what happens to x and y as the parameter t changes. And we're going to try to follow along in the xy plane. So now I'm looking at the xy plane. And when t is 0, then you see that x is 1 and y is 0. So I start at this point, x equals 1, y equals 0. And then t increases. Let's say we're going to track what's happening when t increases from 0 to pi over 4. You see that x decreases from 1 to the value of cosine at pi over 4, which is root 2 over 2, while y increases from 0 to its maximal value of 1 at pi over 4. You see on the right hand side in the xy plane what corresponds to this. Our point moved along as y increases and x decreases. Now if t continues to increase from pi over 4 to pi over 2, then you see that x continues to decrease all the way to 0, while y also decreases from its maximal value of 1 to the value 0. And so on the right hand side in the xy plane we have x and y both decreasing to 0. Now if we keep tracking what's happening, let's say t now is going to increase to 3 pi over 4. As we do that, x is going to decrease to negative values, and so will y, and y is going to decrease all the way to its minimal value of negative 1, while x decreases to the value at 3 pi over 4, which is negative root 2 over 2. When the parameter t continues to increase all the way to pi, then x is going to decrease to its minimal value of negative 1, while y is going to increase back to 0. And therefore we reach that point of coordinate negative 1, 0. Now you see how that works, so I'm going to go a little bit faster for the rest of the curve. Now as the parameter t increases from pi to 3 pi over 2, then you see that x is going to increase back to 0, while y is going to go all the way to its maximum of 1 for 5 pi over 4, and then decrease back to 0 at 3 pi over 2. And so this is what we obtain. And similarly, when the parameter increases from 3 pi over 2 to 2 pi, then x is going to increase from 0 to its maximum value of 1, while y is going to decrease to its minimal value of -1 and then increase back to 0. And therefore this is what we get. So this is, for a more smooth version of the curve, this is the curve that we obtain in the plane.